Hi, this is a video for task 1, responding to student needs. The student voice to me is basically receiving feedback from students. As a tutor, this process is not a one-way process. Rather, it's a two-way sort of thing. So as tutors, we are not just here to generate outputs, but also we need to receive inputs from the students. In other words, we need to know how the student feels about the tutoring, and we need to know if the student thinks that we are actually addressing their needs. And this is very important for us because there's no point for us to teach stuff that the student thinks is useless, right? So feedback is important. And empowering teaching and continual support, I think you can sort of combine them, put them together. So we as tutors need to reinforce the learning process for every student according to their needs and experience anytime and anywhere. So we not just inside of class, but also outside of class as well. We need to make sure the student is undergoing a very reinforced learning process that they can actually absorb. So not just a very general learning routine for everyone, but rather a personalized learning experience for each student. So now I will start with today's questions. So question 1, Shyla fails to understand how the discriminant of the quadratic equation works. She asked these two questions. I think that Shyla is probably given a determinant equation, so b squared minus 4ac in school, and she's taught to use these equations to solve for the number of solutions. But she has no idea what the discriminant actually is and why does it make sense. Like, why is the discriminant positive, meaning 2 solutions? So she doesn't really know when to use the discriminant. That's why she proposed the question, can I use it for cubic functions too? It's a good question, but obviously that tells me that she doesn't know what a discriminant is. So to help solve this problem, I'm going to do this. Right. My first answer to her question is yes. Discriminant is definitely not an exclusive theme for quadratic equations only. Right. So cubic functions also work as well. And in fact, it is used in many other mathematical fields, for example, calculus and linear algebra. Right. In general, the discriminant determines the family of solutions. The discriminant determines the family of solutions. Right? In other words, it is used as an aid to help classify the solutions. So yes, discriminant definitely works for cubics as well, but it's just in a different format, a different form. For the time being, as year 11 students or year 12 high school students, all you just need to know is the discriminant of a quadratic equation. Right? Recall that for quadratic equation, it takes the form y equals ax squared plus bx plus c. And to solve the roots, we have x equals minus b plus or minus root b squared minus 4ac divided by 2a, where a, b, c are real numbers and a is non-zero. Okay. So that's just something we know from the textbook. Yeah. Why does this make sense? You can see that in this equation, we have a square root sum. So we have square root b squared minus 4ac. Well, this has 3 possible solutions, right? 3 possible cases. B squared minus 4ac being positive, B squared minus 4ac being negative and b squared minus 4ac equal to 0. If b squared minus 4ac is positive, that means we have two solutions. Because we are taking the square root of a positive number. Because square root of a positive number yields two roots, plus or minus. Right? We all know that from year 9 or year 10 maybe. If you take the square root, you always get two numbers, plus or minus. Right? So two solutions is positive. Now, what if it's negative? We all know that we can't take the negative. We can't take the square root of a negative number, right? It will give you a complex number, which is not a real root. So if it's negative, no solutions. No solutions because square root of a negative number has no real roots. Finally, if it equals to 0, if b squared minus 4ac equals 0, we essentially have one solution, namely 0. Because we essentially have root of 0 equals 0. Okay. So that's why in the textbook we say if b squared minus 4ac, which we all know now is the determinant, if the determinant is positive, two solutions. If it's negative, no solutions. If it's 0, one solution. Right. So you can sort of derive this sort of reasoning from the quadratic equation. Yeah. So that's where this sort of discriminant comes from. So for the time being, this is all you have to know. Of course, there are discriminants for cubic functions as well, but it's just a more complicated format. Right? But they do the same sort of stuff. They help to classify the solutions. That's question 1. Now we move on to question 2. This student fails to understand the complementary relationships for circular functions or trigonometric functions. She asks the question, what are the complementary relationships for circular functions and when will I ever need to use them? Well, as far as I can see, this student doesn't know the relationship between trig functions, and she probably don't understand the intuition behind trig functions, like the first principles. Where do they come from? For example, going back to the unit circle and even just constructing right-angled triangles. So I think it's very important to illustrate this for them. Now, let's forget about all of the trig identities, that you were given in the textbook. We'll go back to the very beginning, just year 10 stuff. Suppose we have this triangle. Right angle triangle. We know this side is the hypotenuse, right? Let's call that angle x. Then referring to this angle x, this side is the opposite side. And this side is the adjacent side. So what's sine of x? Well, sine of x is opposite over hypotenuse, right? Which is O1 divided by h. What's cosine? Cosine is adjacent over hypotenuse, which is A1 divided by h. But that's nothing year 11, year 12, right? That's just from year 10, year 9 trigonometric stuff. Now, instead of looking at this angle x, let's look at its complementary angle. This angle. What's that? Obviously, it's 90 minus x. Right? So let's compute sine of 90 minus x. Oh, before we do that, let's first define the opposite and adjacent sides for this angle. So referring to this angle 90 minus x, its opposite side is this one. Let's call that O2. Adjacent side then is this one. Let's call it A2. Okay. So we have two sides O2 and A2. So sine of 90 minus x, we all know is opposite over hypotenuse, which is O2 divided by h. But what can we see here? O2 and A1 they are essentially the same side, right? O2, A1, essentially the same side. So instead of writing O2, let's replace it with A1. Yeah, A1 over H. But what's A1 over H? It's cosine of X. Right? A1 over H, A1 over H. That's cosine of X. So hence we establish this relationship. Sine of 90 minus X equals cosine of X. Similarly, we can do the cosine of 90 minus X. We know it's adjacent or hypotenuse. So it's A2 over H. Well, again, you can identify that A2 and O1, they're essentially the same side. So we do O1 divided by H. Well, what's O1 divided by H? That's sine of X. So that equals to sine of X. We have this identity here. Okay. So two identities, cosine, sine. And they are called complementary because X plus 90 minus X equals 90 degrees, right? So the two angles, they make up to 90 degrees. That's why they call it complementary. And similarly, we can derive the complementary identities for tangents as well. Right? So maybe you can try to show me why tangent of X equals to cotangent, which is 1 over tangent of 90 minus X, and why cotangent of X equals to tangent of 90 minus X. Try to use the same sort of logic here and show me why this is true. So that's the derivation of these complementary relationships. When we ever need to use them, well, when you solve equations, most execution is when you try to solve an equation or simplify an equation. When you solve equations, sometimes you are given different ratios. So you are given sine and cosine or tangent or mix of those, right? And that's a bit hard to compute or simplify. So if the angles are special, in the case that they are complementary of each other, then we can convert from one to another. And so we can keep the whole equation in just one ratio, for example, cosine, right? And this will make the calculation much more easier. So that's one typical example where you probably use it. So it is definitely something to remember. And plus, you don't even have to remember it because you can always derive it from the first principles. Okay. So that's question 2. Now I'll move on to question 3. Question 3 looks at Caitlin, who is struggling with a dilation factor. And she's confused why is dilation factor from the x-axis and from the y-axis different. So what I think is that she needs to know what does dilation actually do, instead of just memorizing dilation to stretches the function along the x-axis or whatever. Right? So she needs to know what does dilation actually do, both mathematically and graphically. And I think it is pretty obvious that dilation from the x-axis and y-axis are clearly not the same things, right? It's from different axes. So they're probably not different things. They're probably not the same things. All right, Kathleen, I'm going to show you two proofs. Two proofs to show you why this is different. Why is dilation from the x-axis and dilation from the y-axis different? Okay. I'm going to use some graphical method and use a mathematical method. Let me do the graphical method first. Just give me a while to do a good sketch. All right, so I'm gonna sketch this. X, f of x. 2, 1, 1, minus 1, minus 2. And I'm gonna make that 2 pi. I'm gonna draw the most simplified sine function, just sine of x itself. So it would look something like this. Right? That's just sine of x. Sine of x. Now, alongside this graph, I'm going to draw another one. And this time it will be a dilation from the y-axis. So it will be f of x equals 2 sine of x. A dilation from the y-axis. The graph of it will look something like this. Looks something like that. If you compare these two graphs, they are within the same domain. So the x-axis doesn't change. Instead, we are just stretching the function along the y-axis. So before it was here, now we stretch it upwards, and it becomes here. So for every x value, we double it. For example, if we take that point, we were 1. Now we double it, becomes 2. So if we stretch it along the y-axis, that's a dilation from the y-axis. In other words, we change the y output. Okay, effect is made on y instead of x. Now let's look at a dilation from the x-axis. -1, right? This time it will be f of x equals sine of 2x. So now we are dilating from the x-axis. The graph of it will look something like this. Something like that. If you compare this with the original graph, the y-axis doesn't change. We are still going from -1 to 1. But along the x-axis, you can see that we are stretched, sort of squished towards the y-axis. Right? Before it was here, now we're sort of squishing it, and it becomes a much shorter wave, if you like. Right? So obviously we know the frequency increases to 2, but you can see this is basically a stretch along the x-axis, right? So you can see that a dilation from the y-axis and a dilation from the x-axis, they're clearly not the same thing, okay? One does affect on the y, and one does affect on the x. Now, I'm going to prove it mathematically. I'm going to show you why mathematically this is true. So the most easy one is just by using a trig identity. Sine of 2 theta, sorry. Sine of 2 theta equals 2 sine of theta, right? That's just a trig identity that we order. Then if we substitute 2 theta with x, we get sine of x equals 2 sine x divided by 2. Right. So that's the dilation. Okay. Sine of x equals 2 sine of x on 2. Now, suppose we want to solve sine of x equals y. Then x sorry about that. Then x is sine inverse of y. Right? And let's call it the base angle. This is the base angle. Sine x is the sine inverse of y. Easy. Now suppose we have we have 2 sine of x equals y. Then sine of x equals y on 2, and x equals sine inverse of y divided by 2. Right. So here you can see it's a dilation from the y-axis, because we have a 2 in front of the sine. So it's a dilation from the y-axis. And look, sine inverse of y on 2, sine inverse of y, clearly different. The different things. So we produce different base angles. Right? So at every value of y, we have a different x. For example, looking here, for example, let's take the point 1. Before it was here. Now looking at the same one is somewhere here. It's probably halfway. So at every value of y, we have a different x. Now suppose we do a dilation from the x-axis. We have sine of 2x equals y. Then 2x is sine inverse of y, and x is sine inverse of y divided by 2. Now look, sine inverse of y, those two, they are the same. So the base angle is the same. Hence, we have the same base angle, but it's just scaled by a factor of 1/2. Same base angle, but just scaled by a factor of 1/2. So it changes the x value. All right. So I think the key takeaway is that dilation from the x-axis means stretching it along the x-axis. Dilation from the y-axis means stretching it along the y-axis. Now we move on to question 4. Question 4 looks at integration for areas for functions that's below the x-axis. And we're looking for the area between two functions. I think Josh is proposing that the highlighted area is equal to negative integral from 0 to a f minus g dx. I think that's what he's thinking. But this is not correct in this case, because he needs to understand more clearly what does the integral from 0 to a of f and integral of g actually would give him. Okay. In fact, these two will produce two negative numbers. So essentially, you would have a negative minus a negative number, which is larger in absolute terms. So you have negative plus something, and then you get a positive number. That's basically the logic here. So you don't really need the negative sign. So Josh, I'm going to draw you a diagram to help you understand this. F of x. So suppose we have this function f of x, right, below the x-axis. Suppose I have another function, maybe look something like this. I don't know, I'm just randomly drawing another function. Let's call it g of x. And let's call this point A. So we're looking for this area. We're looking for this area here. That's what we're looking for. So we have two ways to think about this. One way, we can think about the function f minus g. What does that do? Basically, for every value of f of x, it subtracts g of x from it. Okay, that's what f minus g does. So for every value of f of x, we subtract g of x. Okay. Well, between 0 and a, everything is negative. So essentially, we have a negative number minus a negative number, whereas this one is larger in absolute terms, right? Because it's g of x is below f of x, so it's larger in absolute terms, right? So we have a negative number minus negative number that is larger absolutely. So then we have basically a positive number. Right. A positive number. Now, when you do the integration, obviously we would obtain a positive number, right? Which is the area, which is just this area. And it's positive. So you don't need the negative sign at all. Okay. Another way to think about this, we know that the integral from 0 to a of f, this is negative, right? Because f is below the x-axis. So the integral of it is negative. And similarly, integral of g, also negative. Okay. But because f of x is above g of x, this area will be smaller than this area. Right? So the area bounded by f of x and the x-axis is smaller than the area bounded by g of x and the x-axis. Okay. But both are negative numbers. So again, we have negative minus a negative number, which is larger, producing a positive number. So integral from 0 to a of f minus integral from 0 to a of g, which is equal to integral from 0 to a of f minus g, which is positive. Okay. So the result of this integral is positive, representing the area. So again, you don't need a negative sign. So with this type of questions, it's important that you really understand what integration is doing here, okay, and what you would likely to obtain, a negative number or positive number. Right. Now move on to question 5. Dimple fails to understand conditional probability. She gives me this example. Well, I think that he's mixing up conditional probability with joint probability. Both conditional probability and joint probability looks at two events, A and B. However, joint probability is uncertain on both events. So we need both events to occur, but we're not sure, but both events haven't occurred yet. Right? So both events are uncertain. Whereas conditional probability also looks at two events, but we know that one event is certain. So conditional probability is already certain on one event. Okay, so that's the difference. So Dimple, to help you understand this, let's suppose we have two events, A and B. Right? Let's look at one thing called conditional probability, and we'll look at joint probability as well. Conditional probability is probability of A given B, and joint probability is probability of A intersection B. Okay, what's the difference? Difference is that one event is certain for conditional probability, and two events are uncertain for joint probability. Right. So both probabilities want A and B to occur together. But the difference is that conditional probability is certain on event B. So we know that B has occurred, right? We know B has occurred. But joint probability is uncertain on event B. Right? We're not sure if B has occurred or not. And we're also not sure if A has occurred or not. So that's the difference. One is conditional probability is only if you are certain on one event. So in our example, we have two statements. First one, a boy in my class wears glasses. So boy in my class wears glasses. Second one, a student in my class is a boy that wears glasses. So a student in class that is a boy and wears glasses. So let's analyze the components in each segment. A boy in my class wears glasses. What's the certain event? A boy. We already know that this is a boy. What's the event we are looking for? Wears glasses. That's the event we are looking for. So we are certain it is a boy, but we are unsure if he wears glasses. Whereas in the second statement, we are given he's a student. And so we are uncertain whether it is a boy and whether he wears glasses. So we are drawing from a student that could be a boy or a girl, and that could wear glasses or not. Right? So hence the first one is conditional probability, because we are certain this is a boy. And second one is joint probability, because we are not sure if it's a boy. So conditional means one event is certain. Joint probability means both events are uncertain. So you use conditional probability whenever you are given that one event is certain, and you want the probability that both events happen. All right. Finally, question 6. With respect to technology, so use of your graphics calculator. Actually, I haven't been using my graphics calculator ever since high school, so almost 3 years, and I probably already forgot most of the tips for using this calculator. So I probably can't give you very good tips, but here are some things that I can still remember. Some most frequent problems is that you may try to find the maximum or minimum of a function just with the calculate function in your calculator, right? So, but it often comes with an error that you didn't provide the appropriate left and right boundaries, so it couldn't give you a solution. But to solve that, you just set an appropriate window size, so you can visualize the graph properly. Then you can do the left-hand boundaries quite easily. It's just straightforward from the graph. However, this requires experience and general knowledge in general of the domain and the range of this function. Yeah. So you require some experience and general knowledge. But just setting the window size is good enough, I reckon. 2, often you want to solve 2 equations, but again, you encounter the error that you have no valid solutions. Most likely reason is that you didn't check the left and right boundaries correctly. Well, first check your inputs. Are you typing your functions correctly? Yeah. Make sure you have the relevant brackets in place. If you checked for all of those and it still has no solutions, well, check your left and right boundaries, because when you try to find the roots on your calculator, you need to give them a left and right boundary, right? Well, make sure you give good ones. So don't give something like minus infinity to infinity, because that's not helpful. Again, here you need experience and general knowledge, and that's something I can't really teach you. Alternatively, what might be easier is you just graph both functions and you find the intersections graphically, right? Just on your calculator, you can find the intersections, and this might be easier because you don't need to guess the left and right bounds. Finally, when you try to find the area between 2 functions on your calculator, you can simply do integral a to b f minus g. However, be careful with the sign, just like what we did before here. Right? Be careful with the sign of this integral. Right? If you are unsure, you can graph both functions to check whether the integral should be positive or negative, right? And adjust the sign accordingly. So that's some specific tips for calculus topic. Or general tips on using this calculator. Always check if you are using radians or degrees. Always check that before you do a question. Okay. Sometimes that's where you make the silly mistakes and you lose marks for that, which is very, painful. Also, use the answers function. So this one function stores the value from your last calculation. Yeah. So you can keep your solutions from your last step and use it in your future steps. So you can use this to avoid running errors. And maybe on the exam paper, you can just write, for example, 2.81 ... right? Just to represent that you save the decimals in your calculator. Yeah. So just some general tip. And this is it for video 1. End of recording.